So this is me. I'm at Duke, at the Duke Institute for Brain Sciences, so I'm a neuroscientist by day. I'll talk a little bit more about what my lab does as we go on. For those of you who want to follow along today, if you don't already have Julia installed, that may be a little bit of a tall order. I hope you can. I hope most of you who planned on being here went ahead and installed Julia. I recommend you do that from the main Julia page and do it from binaries. It's just going to be easier and it's going to work. By way of advertisement, everything today is going to be with the latest stable release, which for right now is 0.4.6. That's probably going to change in literally like 2 weeks, and when that happens, you should just jump to 0.5, which has all sorts of cool, awesome improvements. And if you've not been doing Julia that long, it's not going to break anything. So that's my suggestion. Everything is up on GitHub, but everything I'm going to be doing today until maybe the last section, if we get to it, is going to be in the console. So as long as you have Julia and the console, that's totally fine. Don't worry about going to GitHub, but everything is there later in notebooks. But I didn't want to assume that you had iJulia installed. All right. So a little bit more about me. This is my lab over here, and a few of my lab people are around for the conference. I am JMX Pearson on GitHub and very rarely on Twitter. Our lab website is up there. We're a computational neuroscience lab at Duke, so we focus on new data analysis methods for fairly large-scale data. A lot of that is from patients at Duke Hospital. I've been using Julia for about 1.5 years. I'm a member of the Julia Stats organization and contribute to a couple of other packages that are out there. So learning Julia is something that I decided to do because I was interested. It's something that came out of my experience trying to write code that would run quickly for data-intensive applications. We also use R and Python in my lab, so I'm conversant there. And my goal today is to give you a discussion of sort of some advantages and disadvantages if you're a heavy Python user and you're thinking about giving Julia a try. So what is Julia? This is for people who have no idea but came in here by accident. Julia is a new programming language. There was a big manifesto in 2012. They just this month cracked the TIOBE top 50 programming languages. So it came out in 2012, a public announcement. The goal, which was stated this year at JuliaCon, is to be 1.0 by the end of next summer. So there's 0.5, which is coming out. The goal is to have 0.6 sometime right after Christmas, and then 1.0 by this summer, at which point things are going to be relatively stable for a long period of time. The people who are the key drivers behind this are at MIT and Julia Computing, which is an organization that offers support for Julia stuff. I have no affiliation with them, so this is not a plug. It's really focused on scientific computing applications, and I think that will be apparent in the sorts of things that we talk about today and the sorts of discussions that go on in the Julia community. Julia really aims to solve the two-language problem. It really aims to get around this difficulty of writing code in a very friendly, high-level language like Python or R, and then when things get tough and you need speed-ups, you need to go to something like Numba or Python or writing extension modules in C and C++. So again, the goal is to be flexible and easy to learn, but within a factor of 2 of the speed of something like Fortran or C++. And I think my experience reading the Julia users list and talking to people in the community is that people come from sort of 2 extremes. One are the set of people that use R data frames every day, and they are really heavy users of statistical methods, and they do a lot of crunching on tabular data. And the other group of people are very heavy C++ users who do high-performance computing on clusters all the time. So it's a bit of a weird meeting because I think those groups tend to have very different needs and very different vocabularies. And Julia sits at the middle of that. So we're going to try to make realistic expectations today for where things are and where they're going to go. And again, we're almost at 0.5. Very, very active developer community, very active community on GitHub. So I encourage you to check it out. I hope it's a good commercial today. Reasons to consider Julia. So if you're really thinking about making the switch, I think if you are in the business of writing algorithms that are data and compute intensive, it's a great language. Mostly because it's just going to be faster than running an interpreted language. If you like to prototype and optimize in the same language. So I think one of the things I'll talk just a very little bit about today, but there are great talks online already about how to do is take your Julia code and make it fast. I'd say one of the most frequent things that comes up on the users group is someone will say, I ported my code from NumPy and it's 5 times slower in Julia. And then there's a process of education of saying, how do you take naively ported code and make it performant. That's not necessarily going to come right out of the box, but it might. If you want zero overhead boilerplate calls, so if you are in the process of using a lot of C libraries and you're using things like Swig to wrap those, Julia is great. It's almost no boilerplate and no cost to call out to C. Very, very easy. And also now C++ as of the last year. Metaprogramming and macros, I won't talk at all about today, but it's fantastic. And if you're not getting to use that right now, it'll change your life. State-of-the-art automatic differentiation. This comes from my interest. We do a lot of machine learning applications, and I think the automatic differentiation in Julia is really cool and is about to get a lot better. You want to use Greek letters and variable names. I do a lot of stats, and I'm not going to lie, I really enjoy being able to use Unicode in my code. It makes things a lot more readable if there are strong conventions for what you're talking about. I think it's an interesting language if you're interested in programming language design. It's one of those languages that, coming from more traditional imperative languages, will change the way you think a little bit. It's a somewhat different paradigm, and that's what I'm going to try to emphasize today. And getting in on the ground floor. I think this is a time when the language is still changing and there are still active debates going on about the right way to do things. And so if you're interested in a language where people really care about the right way to do things and that's not set yet, it can be for you. All right, that comes with some caveats. If you mostly are using or are heavy dependent on packages written by other people, so if you need a complete data frames package and complete Spark integration and all of these things, and your stack looks like 10 libraries that you heavily depend on, that's not where Julia is yet. I think it's pretty typical that you find a package that sort of does it, but it is something where there's a certain amount of sweat equity in sometimes making it work for your use case. That's getting better all the time. But when I jumped in, there is a commitment to understanding a little bit how the GitHub community works and how the package ecosystem works. If you're not really in need of a lot of optimization and your Python code is working well for you, then I think go with what works. If you do a lot of model building, so if you're building a lot of statistical models for things that fit easily in memory and they run in a time you're comfortable with, so I think of this as like a use case where R really shines, it may or may not be for you. Long-term stability is still in flux. So there are big breaking changes between 0.4 and 0.5, and there will be between 0.5 and 0.6. So essentially for the next year-ish, there are still going to be breaking changes in the language. And then there's a 2.0 and a discussion about what 2.0 changes would be. So that pace is slowing, but it's something where I think you need, if you're going to make an investment in the language, to make an investment in the community and understanding what the development timeline is. Because things will break with new upgrades. That's happening. I think it really helps. This is my last point. You don't have to have background in Fortran or C or C++, but it really helps when you're optimizing your code. So Julia is a just-in-time compiled language. That is, the Julia runtime is passing your code to the LLVM compiler, which is Clang, essentially, if you're on a Mac. And LLVM is turning this into machine code. And if that's a complete black box to you and that's not something you're interested in learning, it's going to be hard to make your Julia code fast. Discussions on the users list about how to make things fast are a little bit more technical because I don't think because it's intrinsically more complicated than what we have in Python, but because there are more knobs that you're allowed to turn. So if you really care about eking out the last little bit of performance, it's great, but it does require a little more ownership. All right, so that is my last slide on here, and for the rest of the day, yeah.
What about people who are running into problems with parallel processing in Python due to GIL that,
right.
Does Julia offer some performance from that perspective that might be attractive?
So the question was about people who are running into parallel problems and the global interpreter lock in Python and that being a limitation. I'm going to give sort of my opinion on this. I think the hard part is it's not that Julia has an unclear story on parallelism and concurrency, it just has many of them. So if you go ask on the users list, well, what do you do for parallel and concurrency in Julia? Well, there's a PMAP that's multi-process, there's experimental threading support, there's larger than core shared arrays, there's distributed arrays, and it's kind of hard to make sense of, to be honest. I think that's the problem right now is there is a less clear story around what the workflow is going to be for large and distributed data sets, but there are a lot of options. So you're not bound by the interpreter in the same way. All right, So what I'm going to do is switch over. This is my terminal, and I am going to be in the REPL the rest of the day. REPL, you guys are more familiar with the read eval print loop, so just something that's the equivalent of the console. So on my machine, it's sitting here because I have multiple Julia installs, but you should, if you've got it installed, just be able to type Julia. And I apologize that this is so small. I'm going to try to adjust just a little bit here and see if I can get it to something reasonable. And then, okay. So I apologize that this is the bottom of the screen. Maybe if I do this. Okay, better. All right. So this is kind of the whirlwind tour, and I just want to show you that the things you expect to work in kind of any program language work. So I can, you can use it as a calculator. Julia knows the difference between floating point and integer. So there's a 3 and a 3.0. Division in Julia is floating point division, which of course Python is now on board with, but people still occasionally want to have flame wars about. Other things that are different, power is caret. So again, Julia is odd or fantastic depending on what your intuitions are, and that depends on whether you're an R user or a Python user or a MATLAB user. So if you're a MATLAB user, lots of things in Julia will make sense. If you're a Python user, the conventions are slightly different. Julia has rational types. So this is not integer division in Julia. This means rational division. So you can do things like 1/2 plus 3/4 and get 5/4, and this will be exact. And rationals are baked in. They're already defined in the language. In fact, one of the things that's interesting about Julia is all of Julia's numeric types are actually defined in Julia, including floats and ints, which means you can actually go look at the source code where floating point arithmetic is defined and what that should compile down to in LLVM. If you want to do complex numbers, that's also possible. M is the imaginary unit. So if you're an electrical engineer and like Jay, or if you're a mathematician and like I, everybody can be angry together. One of the things that you'll notice in this output is that Julia doesn't really mind if I put a literal number and a variable name beside each other. This is totally legal syntax and is the same number. So you will occasionally see that. I may or may not remember to do that today. Function calls look like function calls in every other language. So if I want to take the complex conjugate of this number, it does just what you'd think. And if I want to, multiply complex numbers like this, you get the normal stuff. Okay? So a couple of other things that are important, and I got really lazy about because Python is great about. Strings are double quoted. Single quotes are for characters. So if you try to do this, it'll tell you it's an invalid character literal. So this is like C. You can have a character type that's in single quotes, and a string has got to be 2 quotes. So if you're used to double quoting your strings in Python, you'll be just fine. If you're used to single quoting them like me, you have to change things around. Okay? That's all your sort of basic stuff that we're used to seeing. But what most people use Julia for is arrays and array manipulation. So this is going to look a little more like MATLAB. Like Python, I need the commas here. If I don't do commas, it means other things, and I'll show you in a second. This has changed over the last couple of versions. So I have a vector v, and it's going to tell me it's an array of int 64s, which it determines automatically, and we'll talk more about. And it's one-dimensional. And you'll notice that it treats it as a column vector by default. That's also going to be important because Julia, like Python, is a little bit picky in that column vectors are not matrices. And this is an ongoing debate about how to handle row versus column vectors. So that's v. I can make another vector if I do spaces here. That's horizontal concatenation. So this gets really tough to figure out when you're first starting, especially if you're from MATLAB, and those two things should be the same. By the way, if you do semicolons, that's vertical concatenation, and we get the same thing that we had. Now, where this really matters is if I want to do an array, I have to build an array literal, and I have 1, 2, 3, so that's a row vector, and I'm going to vertically concatenate that with another row vector, right? That does the right thing. So you need this combination of numbers and spaces and semicolons to make it come out right. There are also hcat and vcat and all that other good stuff. Speaking of which, a couple of nice things about the Julia REPL that are really, really convenient to use, and these are probably inspired by IPython. If I type a question mark, I go into help mode. You can see I'm toggling that, and then I can backspace to get out of it. It's in help mode. And if I type cat, which is for concatenation, it does two things. I'm going to scroll back up. It does a fuzzy search. So if you don't know exactly what it's called, you can get things that involve that string, and it has the doc string in here. So help mode is pretty nice. The other thing that's kind of cool is if you type a semicolon, then you get a shell. It's not a full-blown shell. It doesn't run everything. But if I want to do, if I want to do an ls, then it'll give me an ls. People have other modes for this, by the way. This is the same way that the Julia debugger works, is to have its own kind of REPL mode. People have done this is something you can actually customize. There is an R REPL mode for Julia that someone built that you can plug in, and you type the right character, and now you're doing R code, and it runs it to an R kernel. So lots of things that I think build on the received wisdom from the Python ecosystem. So we've got these vectors, and the next thing, of course, that you want to do is you want to slice them. So let me just show you what V is. Now, this is either the worst thing I'm going to show you all day, or like a return to sanity. Yeah, so get over it. This has been debated ad nauseum. It just is what it is. It's going to start at 1, so it's like MATLAB and R. The other thing that is more like MATLAB is that the end keyword means go to the end of the array. This is the one I'm sad about, is that negative numbers don't work. There is now a way to index arrays with offsets or negative indices and that kind of thing that is an add-on, that is experimental, but it is mostly for doing stenciling and really high performance like finite element models and things where you really want to run a convolution over an image or a geophysical model and have it do the right thing. That's really the use case there. So indices start at 1. We can use end, so I can do this. End is this keyword that works inside getIndex, and it does the right thing. All right, I also had an array called A. So here's the other thing that Python people need to be really aware of. Julia is column major. So it's in the Fortran tradition, which means you've got to flip all your index orderings when you do loops for things to be efficient, which means you really want to go from the outermost index in. So again, this is a different way to think about organizing your code. For efficiency's sake, if you're doing small code, it's not going to matter. But it is column major. So the entries are stored, going down like this and across. Transposes, again, look like MATLAB transposes. Single quote. Indexing works just like you would think it would. Julia now, if I have an all, a colon operator, will drop any singleton indices. So if you have a one index thing left, that'll get dropped automatically. The other big gotcha, this is really important, it's not my favorite behavior, but the other big gotcha is that slicing returns copies and not views. So in Julia 0.4, you need to use sub. And that's going to stick around a little bit before it's deprecated. Really what you want to do, and there's a Julia equivalent of from future import, and that's what I would encourage you to use because the new syntax in 0.5 is view. So you can ask for a view of an array, and that will not make a copy in memory. So for any of you who are working with large array data, just beware that it's making copies when it does this. Small arrays, that's actually more efficient in a lot of loops, but for large arrays, you want to make sure that you're not copying things around willy-nilly. All right. I'm also happy for people to interrupt with questions, but a lot of this is just syntax differences. Other things that you're used to that still work. Broadcasting still works. So if I add 1 to the array, I end up adding 1 to every element. If I multiply by a scalar, that multiplies every element. Okay? But this is matrix multiply. So in NumPy, all of the arithmetic operators are element-wise by default, and that is not true in Julia. So Julia takes this MATLAB syntax of saying if I want to do element-wise and I want to broadcast, that's a dot in front of the operator. And I'm sorry if it seems ugly because this is now going to be all over the place. Now the cool thing is that this dot notation is really being taken to kind of the extreme and is going to be syntactic sugar in the new Julia for mapping functions. So if you do something in Julia 0.5 of log.a, that's going to do log element-wise. Log is already element-wise in Julia. That's fine. You get the log of every element of the array. But in 0.5, if you have some function that you defined yourself here, this is going to be equivalent of doing map of f over a. So this dot is kind of nice because it's also going to do loop fusion. So for those of you who know what that means, it essentially means it's going to be equivalent to writing code where you actually write out the loops yourself, and the compiler does all sorts of cool optimizations with them. So all this is to really say if you want element-wise, like you're used to in Python, you're going to need to put dots in front of things. Other things that you might want to do. So anybody know the backslash operator? Any MATLAB users? Okay, so this is backsolve. And really what this says is if I do a backsolve x, then the solution to this is, sorry, I should call it b. The solution to this is x in ax equals b. So this is just solving a linear system or doing least squares regression or whatever you want to call it in an efficient way. And that's what this funky backslash is. You also have this one, which if you do a/b is a times b inverse. So let me just show you what that looks like. Diag M is make a diagonal matrix, and diag is get the diagonal. So there I divided a matrix by a matrix. If I want the element-wise version of that, then it's going to fail because they're different shapes. But I can do dot divided by 5, 6. So again, most of this is just syntax. It's just learning how to do the stuff you already are used to doing. I do think one advantage over Python, aside from just speed, is it is a less cluttered notation. There's a lot less namespacing and a lot less verbiage to do things like take transposes and have sequential matrix multiplies. If you do a lot of algorithm stuff, that can be nice. It looks more like things that you're going to see in the textbook, but that's a matter of taste. So that's arrays, and I started with arrays, which we almost never do when we teach Python, and arrays are not quite lists. So in Julia, it's called type of, and I'm going to type type of like 50,000 times today. Yes? Yes.
Presumably it says, oh, it's a 2-element thing, I can write thing. What if you have a 3x3 matrix and a dot divided by a 3-element array?
If you have a 3x3 and a dot divided by a 3, there's a set of rules just like NumPy for which indices get broadcast and in which order. And I suspect, though I'm not certain about this, I'm going to have to check, it's just the opposite order because of the column major. So there's a set of rules, but I would have to look them up to be sure.
Okay.
Yeah. So I'm going to be typing type of a lot today, and as we're going to see, types are a much bigger force in Julia. They're a much more important character set than they are in Python. So A has a couple of pieces to this type, and we're going to see a lot of this today. So A is an array, and the array type takes 2 parameters. One is the element type, which I can get by doing this, and that's an int 64, a 64-bit integer, and it has 2 dimensions, which is what that second piece there is. So A has a type, it has a size, so this would be like dot shape in NumPy. And that's all cool, and I might want to say, hey, let me change the last element, and let's make it 1.5. So this would be like list assignment in Python. And now we get to one of these things that's actually kind of hard, and if you're not used to in Julia is going to be a bit of a pain point, which is that you already decided that this array holds integers. And you tried to assign a non-integer to an integer valued array, or integer containing array. And it's going to complain at you and tell you there's an inexact error because you can't convert that floating point number to an integer exactly. So arrays in Julia, for better or worse, all have types. And so you say, well, how are we doing any better than C and Fortran? Well, there is a way to do this. So if I construct myself a new array, so I have a float and an int, and as you notice on my machine, because it's a 64-bit machine, those are 64 bits by default. You can specifically get the ones you want, but they're going to default to whatever kind of makes sense for your machine. Okay, this guy, it's going to tell you, is a 4-element array, and the type of that array is fairly complicated looking, but as we get used to reading these, it's a complex float 64. There are actually complex numbers in Julia that are only integer valued complex numbers. So this is, just think of this as complex. And then it's a 1-element array. So what Julia decided is what the type that was big enough to hold everything was a complex number, and so that's what the type of the array is. So it's what you would hope it would do. Now, the other thing you might want to do, I'm just going to hit up, by the way, and instead of this, I'm going to add foo, and I'm going to add a character in here. And the type of this, it tells us, is any. And as we'll see, any sits at the top of the Julia hierarchy, and it basically means do Python. This is an arbitrary object. I can't tell you anything about it. It's a pointer to something on the heap, and so there's nothing the compiler can really do about this anymore, but you can have a heterogeneous list. And in fact, if you wanted to enforce this, there is a way to do that, and the literal syntax for that is I put it before the array. And now this is an array of type any, and let's call this b. And I can do b of end equals, some character, and that totally works. So a list in Python is really equivalent to an array of type any in Julia, with one dimension. Yes.
Can any serve as a casting mechanism so that you could reassign A to an any of A?
What you would have to do is construct a new array from this. So I think what you would have to do is, let's see if that works. No, that doesn't work. It's going to be a little trickier than that.
Okay.
I think that's not going to work either. Okay, there is a way to do it. I'm going to try one more thing before I give up. There we go. So I use the constructor for the array, and that constructor takes a parameter, which is any, and then I make an array from B. So you can do it that way. It's very rare. It's not as often a use case as we think it is to have truly heterogeneous arrays, where there's no type, we don't know anything about what's in this array together. And so I've not found this to be a big pain point using Julia, but you can do it. Okay, there are more things that we love from Python only wearing funny disguises. So this is definitely more verbose. All right, so this arrow to 1, this makes what we call a pair. So pairs are these fat arrow things, and I'm going to pass a bunch of pairs. And I am being careful here to make all the keys the same type and all the values the same type. And that's because it is actually going to tell me this is a dict, and the dict maps characters to int64s. So dictionaries can also be any to any, just like in Python, but by default, they are going to be these efficient compiled things that are, I think, hash maps under the hood, and they're going to be typed. So the compiler really has strong guarantees so it can do optimizations. So dictionaries are there. This looks a little bit different, so I'm calling functions on data structures rather than calling methods. There are no, well, Julia has methods. They're not what we're used to thinking of in Python as methods, and I'll spend a lot of time on that. So I can get the keys. That's actually an iterator like we're used to now in Python 3. I can get the values. I can update this in place. This is another just convention. It's not syntax. That, and this is borrowed from Lisp, that if your function ends in a bang, that means that it is an in-place operation and it mutates the data structure it's acting on. So merge, and I'm going to merge my dictionary that I had with one that maps Z to, 26 and Y to 25. All right, so that's dictionary.update in Python. We have sets. The set needs to take an iterable and is also typed. The in keyword also works. By the way, for those of you who use LaTeX, I can hit tab here and do this. That also works. So there are all these aliases for the Unicode characters if you really like the math notation. And S is also typed to be an integer set. We have tuples. Same notation. And let's ask what the type of this is. And again, I'm just drilling this in, that everything has a type and that type ends up being kind of important. Things that you might miss. Plus is no longer concatenation for anything. You can concatenate strings with times, but I think that's going to be deprecated. What you have to do, and this is things that still work, by the way. Some destructured assignment still works that we're used to using with tuples and tuple unpacking. You can't do the full-blown fancy. I can do, this will not work yet, but I think there's a debate about whether it will in the future. That won't work. So not quite as cool as Python here. If you want to concatenate two tuples, and I know this seems like a lot of notation, you have to do this. So the ellipsis, and this is after the variable, is the splat. So what this does is take anything that's iterable right here and turns it into separate arguments. So that will work, and that's actually the correct way to do tuple concatenation in Julia. We're going to see the splat and the slurp operator again when we see function arguments, because again, there's kind of an inverse of this, just like in Python, for packing in arguments to functions. Another couple of things that you'll be glad are around. This 1:5, again, is borrowed from MATLAB and produces something which is like a generator in Python. It doesn't actually create these huge lists. So list comprehensions work. By the way, there is also type inference for these, which has not been great, but is getting better, so that these will also be correctly typed. That's been a weak point. You can do equals instead of in, if you prefer that notation, and that will work and give you the correct thing, which in this case is an array. So I'm going to let A be the first index, and it's going to do these in the order that it makes sense for memory access. The filter clause in Python, where we would put an if at the end of here, does not yet work. I don't think it works. There's been a lot of talk about adding it in. And the last thing that's also easy to do, you do need the parentheses here, and I have to remind myself not to add a colon. String interpolation in Julia is done with $signs, and there's some reasonably sophisticated fun stuff. I do now have to put an end in here, and that'll do my print for me. So iteration works just the same way it does in Python. Actually, weirdly enough, iteration is duck typed in Julia right now. There may be traits eventually, in which case iterable will be a trait. But because it's duck type, it just means if you define next on your collection, it will work as it's supposed to. So very, very similar to the way it's implemented in Python. All right. Questions about this?
the add, is there a simple way to do the add? Not the plus sign didn't work, but if you just wanted to add. Well, not concatenate, just to
Add element-wise
Yeah.
for tuples. There is not a simple tuple element-wise. The most succinct way to do it in Julia is using a couple of functional programming kind of tricks. What you would do is you would map plus over a collection of tuples.
Okay.
So for those of you who are used to doing map and reduce, it is actually quite succinct, but if you're not used to thinking in that way, one of the dirty secrets is that Julia is actually built on Lisp. So if you have an affinity for functional languages, that stuff is there. This is my big advertisement to those of you who care about this to upgrade to 0.5, because in 0.5 anonymous functions are all compiled and really fast as anything else. So you can throw around your map and reduce and anonymous functions, and it's going to be just as fast as anything else, which is pretty cool. Functions also in 0.5 all have their own unique types. So the type system gets extended to functions in a really thorough way. And I'm going to get my toolbar. Okay, and that's actually what's next up is defining functions. So I'm going to go from least terse to most terse, because I think one of the things that's really nice in reading Julia code is it's so easy to define functions because we define a lot more of them than you're used to for reasons that'll become clear. So really dumb function. There is an automatic indentation that happens here. I mean, there's a convention, but I think I've got everything so big it's not doing it. But typically things are indented. And remember, it's okay to have this literal adjacent to this variable. Julia knows what to do. So I need an end keyword. I use the function keyword. I have a name for the function. I have an argument list. This is all pretty standard. And I have a return keyword and an end. We'll talk about this generic function with one method later. Right? And this does what you would expect. Okay? Again, some of you who are fans of functional languages, this will make sense to, which is that it's a convention, if you do say Scala, that you just return the last expression in the function. That's its return value, and no return keyword is needed. And this does just what you would think. So you don't have to put the return there. The style seems to be shifting toward using returns, just I think for readability, but you don't have to yet. Yes?
So is that type anyway? Like, is there a type for X?
There's not, and we'll get to how Julia figures that out. One of the things I'll tease now, it's really tempting when you first start and you hear, oh, Julia's like, it's really tempting to do what a lot of the Python add-ons do, which is specify a type for X, and that's actually the opposite of what you want to do. And I'll explain why. Yes?
Is there a none or no?
There is, but there's almost, it's called nothing. And there are times when you want to return it. It's problematic because if you want your function to be type stable, that is, for a given type of inputs to always return the same type of output, that will screw it up and make it slow. So it's a little tricky in that way. If it doesn't matter, lots of things return nothing, like print returns nothing. So yes, there is, with some complication about it, that may mean things are less fast. Yes?
If we were to generate some Julia code for whatever reason, is there a way to put all three of those statements, the function tripler, the 3x, and the end, all in one statement, all in one line?
I'm getting there.
Okay.
So I'm iteratively pairing away things. So this also works. No function keyword. This is a function expression. And I am just assigning to this name, functions are first-class variables in Julia. I am just assigning to this an expression on the right, and I can convert that, by the way, to a float 64, just so you see that, right? So I can do that, and this is the really terse way of doing it. It's just like one-line function definitions. Here's the function of this, and here's what it's equal to. I mentioned this earlier. I can actually just assign to the name, and this is the syntax for anonymous functions. So if you're used to using lambdas in Python, this is the equivalent in Julia, is I just use the single arrow, and I have a tuple over here, and I have some expression over here. And that will work. Remember, A is this. So that's my quick way to make the equivalent of lambda expressions. Again, those are all first-class objects. They're all fed through the compiler now as of, when 0.5 is stable in a couple of weeks, and that's what you're using. And each function has a unique type, which is useful and for ways I'm not necessarily going to be able to get into. I am going to note that, remember, I didn't type my input. I didn't restrict the type of x to my first element function, so it also works on this. Because strings, just like in Python, can be indexed into. It works the same way as in Python. There's a get index function. So, A2 is really just syntactic sugar for get index A2. And you can define what the get index function means for any particular type. And there's also set index and all the other good things that we're used to from building our own Python classes. Another important thing to remember, this is not as big a stumbling block for Python people, but Julia is passed by sharing. This is going to be a function that zeroes out the diagonal. I'm going to type this and then I'm going to explain something. Multi-line editing gets a lot better too. Say what? There's I do need the end, but I was going to have actual code. Let's see if I can get by doing this. xii equals 0 and return x. And that's super ugly. Thank you. Thank you. That's probably the problem. You can do both. It's up to you. I tend to prefer in because I use a lot of Python, but okay, let's see if I can straighten this out now. The joys of live coding. If this really fails, I'll cut and paste from my notes, and then we'll be okay. There we go. All right. Now, this is the case, and it's not that there's no way to do this in NumPy, but how do you zero out the diagonal of a matrix? Well, if you're writing Python and you're using NumPy because you really want this to be fast, you're writing MATLAB, you've got to figure out a way to get a vectorized function that's going to give you a view of the diagonal of the matrix and then set that to 0. And why? Because the loop kills your performance. Most of the time in Julia, you want to write the loop. Partly because you're feeding this to the compiler that is really, really good at optimizing that loop. And also because in many cases, the code is just clearer because you're not using an obscure vectorized function that somebody's going to have to go look up. Now, where you draw that balance in your shop is kind of up to you, but this is a case where writing the loop is fine. I started out using Julia for time series data where there was simply no way to vectorize what I was doing. And the first day I did it, even making a lot of mistakes, I got a factor of 10 speed up in my code, and I said, hey, it's probably worth investing some time in this. So if I do this, what I'm going to do, because I did return the matrix I fed in. But the bang should be a clue that, oh, what did I do? Oh, because A is not square. That's it. There we go. I didn't check my bounds access, which is a no-no. So here, this is B, and B is zeroed out, but A is also zeroed out. So this works just like in Python. It's a very verbose example to show you that if you pass in an array, that array is not copied. You're actually, if you're doing something to it, mutating the original input. So that's FYI to be careful about, is like any numeric programming language where you're swapping around arrays, you need to know whether things view or copy. And this is a pass by sharing. So you really do have a pointer to that array sitting out there.
So if you do one loop, then you really have to put that number of
You do, but Numba doesn't work on everything, right? Yes, so I mean, Numba's great. Like I've used Numba, and Numba's coverage of NumPy is really impressive now. But there are still some things it doesn't do, and I would say the advantage of Julia, and I'll get to this in just a second, is that if I want to use Numba really effectively, I need to write it like C. All my arrays need to be allocated before I call that function, and all my arrays need to be typed. And so if you want to actually have reusable code that works for both floats and ints, you're going to have to write two functions. So there's a little bit of savings there. But yes, I think anything Numba works on should be comparable performance, right? Anything that's like Python should be comparable performance. Julia just gives you some of that for free. Splatting and slurping, which I mentioned earlier. So if you have a varargs function, so function, I'm going to call this parser, which I checked and is not a reserved word. Variable and a value and a rest. So there's my ellipsis. So this function is not going to do anything interesting. It's just going to print some things. Again, this string interpolation is really handy. By the way, it really is possible that you would write a little something like this because Julia code is actually a valid object in Julia code. You can write macros that rewrite code on the fly. And it often is the sort of thing that you would want to do string interpolation to write new code that then gets spliced in at the point of call. Macros in Julia are a huge part of what make the language cool, and I just don't have much time to go into them today. So if I do something really simple, by the way, I also love that Julia has symbols. This colon before the identifier is a symbol, which is often what we're trying to do in Python when we have string keywords to dictionaries and other things. The symbols are useful because you have to work with Julia code, and you need to know the difference between I have a string that says X and I have a variable that's called X. So I have a symbol here, and then I've got 5, 7, 8, and foo. And X is variable name is X, and the value is 5, and everything else that's in that ellipsis gets put into an iterable. So just like in Python with the asterisk in front of args, we're slurping all these things up into a single thing that we can then iterate over and do what we want with. The other thing that you often need to do is to do the inverse, which I've already shown once, but I can show again. So I'm going to make a function that gives you a random matrix that is like the matrix you passed in. That is, it's going to have the same shape, etc. So something like this, and I want to return rand. And rand will not take a tuple as an argument. You need a series of arguments, and that's easy to do if you just use this operator. And that's going to splat that out into 5 and 5. So any time that I need to take something that's in a collection and string it out as a series of arguments, this is what I do. So you tend to do this a lot. There's a little less effort made to have all the possible interfaces for everything, so this is kind of how you have to put stuff together. Defaults and keyword arguments. Mostly like you would think, this is the LP norm for those of you who do a lot of math on this. Again, element-wise, power. So what I'm doing is I am raising whatever x is, each element of it to the pth power. And of course, this works just fine if x is a number. And then I'm going to take the sum of that, and I'm going to raise that to the 1 over p. So it's the pth root of the sum of the x's to the p. So we're used to this being 2, which is the standard norm of a vector. So 2 is a pretty good default argument. So if I do this, I get a sensible number. And just to show you that, that's why I had it. It's equal. You can figure it out. And you can obviously specify that this is something like 3 or 1 or whatever else. So default arguments work just like they do in Python. Keyword arguments, there's a wrinkle. And there's a wrinkle with default arguments I'll get to later. But I'm going to paste this. Oh, that's really unfortunate. This is a function called makeCircle. It doesn't really make a circle. It takes 2 inputs, x and y, a radius that has a default of 1, and what I want to draw your attention to is the semicolon. Keyword arguments all go to the right of the semicolon. And there's a reason for this that we'll get to that has to do with multiple dispatch. In Python, you can basically do any combination of things that's unambiguous and it'll work, which is beautiful. Like the Python system for this works really well. In Julia, the cost of the way that Julia does dispatching on functions essentially means that you have to segregate your default values and your keyword arguments. So let me show you what this means. I am just printing a bunch of stuff. So here I'm using all my defaults. It says it's a black circle of radius 1. My radius argument was a default argument, so I can do that by position. And I can even do this, because color is a keyword argument, and the radius will default to whatever it defaulted to. But what I can't do is give it a radius. By the way, notice I did not need the semicolon when I called the function, only when I defined it. And I'm going to get rid of the keyword here and give it the last keyword argument. So no keywords given, but I'm actually calling the function with all the required parameters, and that's going to fail. So keyword arguments mean keyword-only arguments. So that's a trade-off in usability, and take my word for it for 20 minutes until I show you why it's that way. So the interesting thing is that I defined a function before like this, and I'm just going to do another one here that gets the last element. So this function returns the last element of something for which get index is valid. And it works for a whole bunch of things, right? So if I give it a range, it works. If I give it an array, it works. And if I give it a string, it works. The problem is that, remember I had my doubler function that just multiplied it by 2? This is, of course, going to fail, right? It makes no sense. I cannot multiply a string by 2. Well, you can in Python, but you can't in Julia. And the problem is that we've got 2 major issues that we need to solve here. I would like my doubler function to handle cases of multiple different types of input, which we often run into. We want a function that handles different classes of inputs correctly. But I would also like to be able to extend the behavior of functions that I did not define. So if I define a new type in my module and I want doubler to work for it, this is traditionally pretty hard to do, and there are a couple of ways that you solve it, and one is by subclassing, right? So I want my data structure to have a behavior that is similar to another data structure, but I want to special case it, so I'm going to subclass, and then I'm going to override that method. Now the hard part is, what if I have something like fit for a couple of different model classes, and those models have nothing to do with each other? Like there's no is-a relationship, and I want to call fit. Well, I can define it, and it's called the same thing, but if we want to extend something, it's really a drop-in replacement. It's not our function. We would like a way to solve that. So those are the 2 problems that I'm going to come back to. We're going to talk about types first, and then we're going to come back to how Julia solves this problem. All right, questions before I move on? All right. So types matter a lot in Julia. And there's a great article about this that people talk about in the sort of functional versus object-oriented debate. And it's the Steve Yegge article, Execution in the Kingdom of Nouns. Object-oriented languages, particularly like Java, which is the one he's writing about there, everything is a noun. Everything is a class. In Python, everything is a class. At least in Python, you can have bare functions. The flip side of that is the sort of functional world where you have data and you have behavior, and those are really 2 separate things, right? So you have a tree and you have a list and you have an array, and those are data, and you define your data in one place, and then you define all the behaviors that you can use on those data in other places. And those are considered separate. We have a well-defined data structure and then things that you can do with it, and all the action really comes in the things that you can do with it part. Julia is really in that camp. So Julia is very inspired by things like Lisp and Haskell, and so Julia is a type system, not a class system. What that means in practice is Julia types don't have methods. We do have methods, they're functions, they're bare functions, but Julia types are what you call plain old data. So it's like a C struct or a MATLAB struct. So just to show you some things that we've already kind of seen, one is an int64. Keep typing type. Type of one is a float64. Like I said, you can get float 32s if you really want them, if you're doing GPU computing. So type of is really handy when you first start learning Julia to just get the sense of like what the types of things are. In the same way that if you were running a new library in Python, you would figure out the types of things, like what class is this, what class is that. Right, this is different, that's an ASCII string. ASCII string is disappearing, everything is just going to be string now, eventually. And I'm going to get my A matrix again. And I've already talked to you about this. A is an array. That array type is a parametric type, and I won't probably get to talk about that as much as I would like today, but this is what makes really generic programming really amazing, is that the element type, which is float64 here, can vary, and the number of dimensions can also vary. And Julia is really great at handling not just variability in the former, but variability in the latter, being able to write one function that handles vectors, matrices, and 5 and 10-dimensional arrays with the same code. So in fact, in a normal language like C or Fortran, you would have to write a number of loops corresponding to the number of dimensions of the array. In Julia, we don't have to do that, which is a real time saver if for some reason you have these different dimensions of things that are going on. So again, I showed you can get the element type of A with this function. Indims, by the way, is the other one. Types in Julia are just other variables. So T is float64. The type of T is data type. The type of data type is data type. So the type of operation stops at data type. So there are no built-ins, right? So if you want to ask what the type of string is or something defined in C in Python, it's a little bit different than a class you define yourself. In Julia, you just kind of circle around when you get to data type. So that's one kind of way through our type hierarchy, and I'll show you the other one in a second. Super on right now, it's going to become super type to be consistent in the next version. So if I type that, forgive me. The super of float64 is abstract float. The super of abstract float is real. And we get to any. And the super of any is any. So we circle around, so the super operation also takes us up the type hierarchy, and it circles at any. So that's the top of the type tree. Now, here's the place where you've got to get a little bit of a mental model. So in Julia, it really is a tree. There's no multiple inheritance. There's not really any inheritance at all. But types are organized in a tree. Any is at the top. You can have multiple children, but every type only has one parent. Only the leaves of the tree, only the nodes, only the types with no children are concrete. And variables can only be concrete types. So this is a limitation. You cannot instantiate a variable that is real. You have to instantiate that variable as a float or an int. You can have a container of reals. And what that container is a container that says, okay, compiler, I can guarantee you that everything in this array is a subtype of real and behaves like a subtype of real. So what this means is that as you're kind of figuring out your problem domain, you'd have your sort of UML diagrams of various ISA relationships. that you kind of have to figure out what the bottoms are because there's no inheriting behavior. You define it for, well, sorry, I take that back. You can inherit behavior, but you realize that the only things you can instantiate are at the bottom. So you really need to kind of get your tree right. That's not ideal. There's a lot of talk about having traits, things like iterable and indexable and those sorts of things, but they're not in the language now. There are some add-on packages where you can do that, and that'll make this a little more flexible. So that's what the folks at Rust have done. Haskell makes this a little bit easier, and that seems to be a solution that the community really wants, but it's just not implemented yet. So right now, you've got a tree, and at the bottom of the tree are the actual concrete types. Yes? Say what? Ah, good. So it's below number, and subtypes, by the way, get you the subtypes. And there are no subtypes. Complex is a parametric type. So I'll show you what this little, I don't know, super smiley face here means later. Complex is a parametric type. You can have a complex number that has essentially elements of any real type. So you can have a complex int and you can have a complex float. So it's a little, I mean, that's a decision that had to be made, and this is where they ended up having it. So complex is under number, and you kind of tell complex what the two elements of the complex number are. And they have to, what this means is they have to be subtypes of real. So if you want the rest of them, so number only has complex and real. And real has abstract float, which is all your floating point numbers, integer, which is the abstract type of which int64, int32, and int, which is just an alias for whichever of those your machine is using, are all types of. There's an irrational type, which is for defining certain symbols like pi and e, so that they don't have a type until you make them interact with something. You don't want pi to be float64, and then you multiply it by a float32 and you get a float64 back. It's for things being able to have guarantees that the type will stay float32. And then there's the rational type, which remember we saw the double divide gives you rationals. And again, rationals, you can have an int32 numerator and an int32 denominator, or an int64 and an int64. So rationals can be differently typed also. Other questions?
Is there a concept of unsigned integer?
There is. So the question is whether there's an unsigned integer. Yeah, so there's a big int, which is arbitrary precision, Boolean, signed, and unsigned. And those are all, I think, abstract and come with a number of bits.
But it's built in.
Yes, yes. Other fun things, if anybody's really into like arbitrary precision computing, like people have packages for arb floats and unums and all these things that actually get away with, there's no floating point error anymore, you get a range back. So it's super cool. People are using all these things. Those, by the way, because they are defined in terms of basic Julia types and they're defined in Julia, have the same performance and are defined in the same types of code as the ints and the floats. So defining new numeric types is really easy, and I may not get there at the end of today, but there is an example in GitHub of defining a new number type, and the amount of code is, you know, below 20 lines, and you can do things like backsolve, and it just works. A little more syntax. This is kind of asking the same thing. This is the subtype operator. Is float64 a descendant of real? So we had super and subtypes, which are just adjacent. You know, what's above me and what's below me. This is transitive, right? So that gives us a relation among types. If we have instances, we can use isa. And yes, one dot is a floating point number. The convert method is pretty handy. There are multiple ways of doing this, and you've seen me do this in other ways, like calling constructors. But that works. The other way that I'm talking about is just doing that. Constructors fall back to convert if they don't know what to do. So there's all that stuff. If you want to find out if a type is concrete or abstract, it's isLeaf type, which is a little bit unintuitive. And you can probably tell by the name that that's going to be a false. Yes?
So context is not super type of int or float, right?
Yes, that's correct.
So how system understands that, for example, we have an array of integer complex and no real complex, real float, how it recognizes that you need to create an array of complex float.
What's the question?
Yeah, so the question is, if I have let me make sure I understand. If I have an array of complex numbers, and I have an array, so say complex where all the pieces of the complex are integers, and I have an array of real floats, and I want to multiply those, how does it figure out what's going to happen? Is that correct?
No, I just initialize an array with complex integer and float, not complex float. And it gives me complex float array. How it recognizes.
So
Yeah, kind of.
So this works. So maybe we should talk offline because there are mechanisms that are built in for saying how you convert from one to the other. So I might have misunderstood. Again, there's an example, and I hope we'll have time to get there in my last chunk of the day for how you define the rules for what things get promoted to what when you're doing arithmetic. Okay, parametric types, and I have to cover them because arrays are like the single most important type in Julia, and they're parametric. So let's see. Okay, my A matrix is still this random thing, and this should be true. Interestingly enough, and I'm not going to get into the weeds about this, this is also true, that A is an array with float 64 elements without specifying that. So it's sufficient for me to just say is an array that contains float 64s. That will also return true. In fact, this will also return true. So there is something about the type system that you can read more on in the documentation to say, yes, this kind of thing works. These sort of set relations. A is an array. A is an array of float 64s. A is an array of float 64s with dimension 2. So that all makes sense. Reshape kind of works like you would expect. I'm just making myself some integers. Right, same thing. So A and B are both members of the class of arrays. And so any function that we can write that works on the class of arrays should be able to work on both A and B. So I'm going to redefine. So I had a last element function, remember? I'm going to call this last L just so we don't clobber it. And this is what I would do. So I do have type information now, but it's as loosely typed as I can make it. A needs to be an array for the following thing to make sense. So I've now given my function some type information. I've said this only applies if A is an array. So the 2 colons are my sort of type specification because that's the class for which this makes sense. Now there could be broader classes. This won't work for a set or a dictionary, but it would work for a tuple. So I've not defined it as widely as I could. If there were a trait called indexable, that's what I would define it on, right? And in Python, this is just done with duck typing. We just check and make sure that we can call getIndex, and then we do it. This is more powerful, I think, and we're going to sort of see why. So, it works for this, and it works for this, right? So just like you would think it would, but it's going to tell me here there's a method error. It's going to tell me last L has no method that takes an int 64. Reading these error messages really becomes an art because when it can't find a method, and there are many to choose from, as we're going to see, with the same name, you have to learn to kind of parse through and figure out what arguments are matching and which ones aren't.
Why is an error message find something?
We'll get there. It's because there could have been 50 functions named lastl, and none of them matched. So that we're going to see is the key thing with multiple dispatch. Lastl is not a function; it's a generic function, and we can redefine it as to have as many cases of inputs as we want.
It becomes an interface.
Trying to think if that's the right way to put it, but it is something where we define how it acts on all the data types we care about. So let me give you another example of this, where the restriction to array may not be sufficient. So more notation. So this less than colon notation you've seen before, what this curly brace after the function name tells you is that this function is going to have a type parameter. That is, I'm going to have a variable in the function definition. That variable is a type, and that type can only be a subtype of number. And the input that this function is allowed to take is an array with element type t. So it is possible that in the future this is going to be more succinct, and it's going to look like this, which I think is a little clearer. This tells you it will take any array where the element type is a subtype of number, but you can't do that today. So here's to the future. So what we have to do is forward declare we have this variable type t. T has to be a number, and this is going to work on any array that has numbers in it. And I'm just going to do something silly. And that's because diag is determined on arrays, and sum has to have numbers to make it work, or at least that's the case that I care about. Maybe there's something else for which this would work, but I'm defining it for this class. I'm defining this function for this class of things. And so I can do, diag sum on A, and then I'm going to paste this thing in. I'm going to make myself a character, an array of characters, just to show you that it fails. So I'm using an array comprehension here, and I'm reshaping it. So there's C, and it tells me again I have this method error, and it says there's no version of diag sum that takes an array of characters. Okay, this is the biggest gotcha. So if you go look at the things to be aware of on the Julia page. All right, here's our old friend A. A is a float 64 array with 2 dimensions. It has a float 64 element type. I feel like I'm a magician. You set this thing up for a punchline. All right? So is the type of A, is basically what we're asking is A an array of real elements? And you would expect it to be true, but it's not. And there are various technical reasons for why this has to be, and I've got a link on my pages on GitHub that you can go read the discussion. It is not actually from the type system, it's so that the compiler can make guarantees. And the reason is that the compiler can't do much with an array of reals because they're not concrete, because they can't tell if this is going to be ints or floats, and you really want the compiler to know if you're dealing with ints or floats. So this doesn't work. And so as a result of that, you have to write it like we did up here, where you have this type parameter out here. You can't just say it takes an array of numbers. So that's the technical point, is that you actually have to say it takes an array, and you have to restrict the element type rather than saying array real. So remember above, just to make really explicit, we had that A in our function had to be array T. And the question is why we couldn't do array real. And the answer is because that doesn't match in the type system. You have to have the parameter here, because what that does is say essentially for all t, does it match any of the t? So mostly right now, just think about that as notation. There is an exception. Tuples are also parametric types. They're actually, they have as many parameters as your tuple has. And you do have this does work. So the technical term is that Julia's containers, its type parameters, are invariant, but the tuples are covariant. And the reason tuples have to be covariant is because the argument to your function is a tuple. And so the tuple of arguments you pass to the function has to be able to match, or if you had something like this, and you gave it an int and a float, it would never be able to match it. So this just has to work this way, because there are plenty of functions that should take two real numbers and work and be fine. So tuples are the exception to this. So unfortunately, in Julia, this is part of the baggage that you learn in thinking about writing efficient code. The next thing I'll show you is about why this is useful and helpful and leads to kind of more succinct code bases. So questions about the type system before I move on? Because we're going to be using this again and again. Yes? There are. I'm not as well versed in them. So I'll show you one small example with IO streams. The question is whether there are other types that are really important. So yeah, IO stream types, and there's a whole set of interfaces there. Strings, and how strings handle Unicode and all the other things that are important there. And people tend to define a lot of their own types depending on what package they're working with. So it's a little bit analogous to asking, are there important other classes? And the answer is absolutely. Yes?
So you could define a structure that's like a tuple and say this structure is a coordinate pair as opposed to just two numbers.
Yes.
The type system will honor that and say, no, I don't take any random pair of two numbers. It has to be a coordinate.
Yes. And you would do it, you would write a function. And in fact, that is the example in the types documentation page on Julia, is having a point that's two numbers. And it would have to match this. It will not do that conversion implicitly for you. You would have to say, convert this to a point. So it's willing to be that pedantic.
So with the way you dispatch functions, we have to work that way.
Yeah. And it's also so that you can do validation, right? If certain sets of pairs, even of floats, are not valid, then you can do all that validation internally. Yeah. Yeah, so if you call it a point, and even though it's on disk, it's like two floating points, and the compiler packs it in as two floating points, the type has to match for what I'm about to show you to work. Okay, so let me come back to this question in multiple dispatch. That is, we want functions to be able to handle many different combinations of input and maybe be called the same thing because it's clear. And how do we extend functionality we don't own? So the example we had before was this diag sum. Helps if I spell it right. And it was a generic function with one method. In reality, we probably only want to define that on matrices. So I'm going to go back and I'm going to actually quit and enter Julia again so that I can cut and paste this. This was the same function I did before for diag sum. I'm going to be a little bit pickier. And that is, I have a 2 up here. I have an array T2. So I'm going to require this be a matrix and that it's an array of numbers. So that 2 right there. Okay, it's a generic function with one method. My favorite random 5x5 matrix. And I get a sum of the elements on its diagonal. This will fail if I give it a list of 7 random numbers. Because again, it's telling me that there is no diag sum that takes an array of float 64 that's one-dimensional. So we only defined it. This is not a surprise. We said, hey, here's what you do in this case. But we might want this thing to have behavior. We could pick multiple things, right? What we could do is we could decide if the matrix would be square, that we're going to broadcast this, and then we're going to take the diagonal. It's up to us. So I'm going to pick the simplest behavior, and I'm going to do this. Remember, I'm going to have this restriction that the element type, so t is a type parameter, it needs to be a number, and v is now a vector. By the way, vector and matrix, you'll see in a lot of Julia code, they're just aliases for arrays of dimensions 1 and 2. So I could easily have said array t comma 1. And I am just going to make the diag sum of a vector the sum of that vector. And now what Julia tells me is the diag sum is a generic function with 2 methods. This is how Julia does behavior. There can be a lot of versions of diag sum. It will call the correct one based on the type of inputs you give it. So the types are crucially important because the types determine what version of the code gets called. And while I'm at it, if I have a singleton, the diagonal sum is just going to be that number. Okay? So I can ask, so now this works, and this now works. Now, the interesting thing, because debugging obviously becomes harder when I have 50 versions of the same function around, I'm going to show you one of the few macros I'm going to show you today. So macros in Julia all have an @ sign. And the @which macro is pretty cool because it's going to tell you which version of the macro gets called and which version of the function gets called and what line it's on. So I put this in at the REPL, so it's not going to have good line number information, but if you do this in, say, the notebook, it'll tell you what input you defined it on or what line of your source code, and it's going to tell you it's calling the version of diag sum which is defined with 1 argument, which is a number.
What does the none represent?
I think it's just because it doesn't have line number information. The question is what none represents, and because I typed all these things in the console, I think it's because it doesn't have line number. Yeah. So this tells you it's calling the version for vectors. The only reason you need to know this is because it may not always be obvious to you what type of something is returning, and if there's ever an ambiguity in what kind of type it is. So imagine that we have functions that are defined for number and functions that are defined for real, 1 argument each. That's easy. The most specific function signature always wins. If you have a function that has 2 arguments, one of which is real and the other is number, and a function with the same signature but one is number and one is real, that's an ambiguity. And Julia will complain at you and tell you that what you need to define is a function with a type signature real and real, because that will be more specific than both of them. Or it'll say it has to be real, real, or more specific. So as you would imagine, anytime there's an equal level of specificity in the code, you're going to have to resolve that. The reason that you have things like @which is so you can make sure when you get ready to call with a certain set of arguments which version it's going to, because that just comes up in debugging these things, especially if you're extending behavior you don't own. Now the beautiful thing about this, as I'll show you, is I can import behavior from someplace else, and I can just define it to work on my new type. And everything works, right? I've just added one more method. So to show you, if you're ever curious what the methods are, you can ask, and it says there's 3 methods for this generic function, and these are their call signatures, and it will tell you what lines they're defined on. And if you really want to have some fun, you can ask how many addition methods there are, and I can tell you, because that scrolled by pretty quickly, that there are 171 definitions for addition. One of the reasons the type system is organized as a tree, I don't think it's primarily for this reason, but you have to be able to do type inference really, really quickly to figure out what these are. This goes back to another point I mentioned earlier, and a crucial point for understanding why I'm putting declarations in certain places and not others. We have this function that's a doubler. It's a generic function. It has 1 method. And we showed that if I give it an int, that's fine. And if I give it a float, that's fine. And you might say, gosh, like I've been using numba, and I know I'm going to get really a lot better performance if I tell Julia that what I really want here is an int, like an int 64, and then I say it's 2x. Don't do this. And here's the reason. You should only give Julia type information that is as narrow as possible for which the behavior is well defined. So remember I had something earlier that only worked for arrays. I should restrict it to arrays, but don't restrict it anymore. Because the point is that my code here works for anything for which multiplication is okay. What Julia actually does is the first time I call doubler1 up here, Julia takes my function, it figures out with dispatch, oh, it's got to go to doubler, there's only one there. It says, what is the type of the argument? It's an int. And then it compiles a version of this function for an int. And when I call it with a float, it compiles a version for a float, and those are cached. And from then on, they're compiled code. So what you should assume that Julia is doing is every time you call it with a new set of types, it's compiling a new version that it's got around. So the only reason you need to worry about giving it type information is to restrict the inputs of the function. And for semantics, it can compile 15 different versions for a function that only has one method, depending on what you feed in, and that way it's only on an as-needed basis. If you never call this function for an integer, you never pay that penalty in overhead.
So what happens if you say method's done? You don't see those two methods.
No, because those are not considered methods. So the question is, why don't I see these extra things? It's because they're not considered methods. They're compiled blocks of code that the dispatcher just sends to. So there's a difference between the method phase of it and the compiled code phase of it. And Leah Hansen has a really nice blog post sort of going through the steps that Julia runtime goes through when it compiles your code. And it's really cool reading because there's like 5 or 7 different steps.
What if you get certain amount of probability about this?
In principle, that's possible, but you sort of have to say, the question was, what if you're concerned about having all these cached versions of functions around? There's only one cached version for every different method signature. So if you were calling, if you're calling 50,000 different versions of a function, you might be in trouble. I think in practice, we only tend to call 5 to 10, maybe. It could be a problem. I haven't run into it personally. There may be some optimization I don't know about in that case. Another caveat about I could obviously put 0 here. Now there are 2 methods. Now all I did was define doubler to have a default argument. In Julia, this is syntactic sugar for defining this and substituting 0 on the right-hand side. Default arguments actually compile new methods. So I would be careful if I had like a plotting library that had 50 defaults in here, because then you will get the combinatorial explosion of all those defaults. So that's the case in which you really are better off using keywords, because keyword calls don't get cached in the same way. They're a little bit less performant for that reason. So the question is, how does this get used? And the answer is everywhere. This is the organizing principle for Julia code. That is, instead of writing a big function that now is going to be more, if it's not closed source, it's not easy to modify for people who are using my library, where I special case every potential type of input, because I don't have a self keyword to dispatch on. I instead dispatch on the type, and I define one version of my behavior for every type. This makes it really easy to define new numeric types, and it makes it simple to do things like binary operations. We've lived in this world since C++, where every time I want to define plus for a new data type, I have to define left plus and right plus, if it's commutative, and maybe if I just want it to work different ways. And now I have to define my type kind of intersected with anything I would ever want to multiply it with. And then, if somebody else wants to add something to that, they have to subclass, which is kind of hard. In Julia, plus is a function. You define it for whatever you want to do, and there are a couple of things built in that people have been asking about to make that process a little bit easier. So, I'm actually going to get to my last thing. Yes?
Is there such a thing as units that you could, so we don't crash a satellite into Mars again because of one team working in in kilometers and the other working in miles, is there a way to enforce at this
Right.
definitional level that the units we're working with are?
Right. So the question is, do we have units? And the answer is there's at least one package, and there may be two that handle that. And they sort of build kind of units in as a type tag. Well, I don't know exactly how they do it, but you can fix units. So that's there, but it's not part of base. There's a big effort in Julia community right now to slim down base. There's the sort of MATLAB view of the world where, when you start up Julia, you should have like 500 functions in your namespace. And I think the trend has been more toward the Python and R view of the world where there's kind of a slim thing that starts up quickly and then I import a lot of the things I need. So a lot of things are moving out of base right now. Because of the focus on numerical computing, Julia is a general purpose language, but the community around numerical computing is much stronger. And so everybody wants to see their favorite method already ready there in base. We don't have to import it. Typing that one line is a big tax. So what I want to do for the last thing is probably bring over a piece of code. And it's unfortunate because it's more typing than I want to do with the REPL, but it is a more sustained chunk. And I want to walk you through how you would start to do this. So let me see if I can. I think what I'm going to do is quit out of here. And I'm going to pull up a piece of code, and I will make it large, appropriately large. So what this example is, oh, that's terrible. And does anybody know how to get rid of the sidebar on this?
Toggle tree view?
Thank you. All right. And let's make that bigger. Okay. So I want to show you a little more extended example, and extended is not really the word. This is under 30 lines of code. This is inspired by a really cool package in the Julia ecosystem called forwarddiff.jl. Forwarddiff is a package for making automatic derivatives. It's a really nicely integrated package. The same author is in the process of writing something for reverse mode differentiation, which is also called backpropagation if you're into neural networks. It's really, really fast. It's very competitive as a package. So this gives you a little bit of a sense of how you can do something like build automatic forward derivatives, which are not as performant in the case of neural networks, but are cool because you can implement forward derivatives with a numeric type. So again, I'm not talking about taking a function and doing what we call finite differencing, which is evaluating at 2 points and taking a difference. This is the correct derivative to machine precision, and you do it simply by, in Julia, saying this is a subtype of real. Any function which will take a real number as an argument, the derivative gets spit out. So it's a really cool thing. This has been around. People have done this before. It just turns out to be really easy to do. So I want to kind of walk you through how you would do this. So the question is how you define a custom type and make it play nice with everything. So the first thing here is I'm going to define my type. So this immutable you should just read as type. There's a type keyword. Type says I'm going to create a new type. Immutable says I'm going to create a type, but it's not going to change. So what that means is that my fields don't get to point to anything else, and this is better when you can do it because you can stack allocate and things are fast. So it's immutable the way strings and floats and whatever else are immutable, and there are better compiler optimizations. I give it the name for my new type. These things are called dual numbers, and it's going to be a subtype of real. So that's where it's going to sit in the type tree. This is mathematically false, but computationally awesome. These things are not real numbers. They're generalizations of real numbers. They probably have a more sophisticated actual mathematical definition. And my type is going to have 2 fields. It's going to have a val field and an adjoint field, and I'm borrowing this from reverse mode differentiation, so I'm not claiming that's correct either, but they're just 2 numbers, and they're going to be float 64. So this is how you would define a type. You would say, hey, here are the fields in my type, they've got to be data, and these are the types of the fields. This is the reverse of function definition. Function definitions, you should type as widely as possible. If possible, leave off all your type information. And Julia will specialize for you. So for the widest type for which behavior makes sense, that's what you restrict your function to. Types themselves, it's the opposite. And the reason is because I want the compiler to be able to actually convert this to raw bits, and it needs to know what the layout is here. So the golden rule for performance is no abstract types inside this declaration. They need to be concrete. Sometimes you can't get around this, and that's fine, but to the degree you care about allocating millions of these things, you want concrete types here. So I've just decided these are going to be float 64. There's a way to define a parametric type here where dual could be a container, and it could have ints here or floats or whatever else, and it would then have a type parameter. And if you look at the actual forward diff.jl package, that's what Jarrett does. And it's a really clean example of this. So what I've now got to do, and this is like the same way that you would have a class in Python that does, dunder len and double underscore repr and all these other things, I'm going to kind of make the type play nice. So I've got to override base.show. So this is the standard namespacing. I could have also done import base.show, and then I just would have said show here. Julia is a little confusing in that it has import and it has using and it has maybe one other thing, and it all depends on what you have to put the namespace in front of and what you don't. So I refer you to the docs. Here, show takes an IO object, and it's going to take a dual. Again, show is one of these things that has like 100 methods, right? I just create a new method for show based on my type, and I'm just going to say, oh, all I want to do is print a string that has the val, and it has the string that's the adj times epsilon. So the definition of these dual numbers, by the way, is it's a plus b epsilon, so a little bit like complex numbers, except for complex numbers, I squared is -1, and for dual numbers, epsilon squared is 0. So you should think of it as like being a tiny little infinitesimal that you're using to take your Taylor expansion. And the rest of what I'm going to do here is define arithmetic on those guys. So I define show so that it just has a nice thing that prints out. That's really all it is. And then I'm going to define a couple of convert things. So this is something somebody asked me about earlier. Convert says, and this is a lot of syntax. What I'm trying to tell it how to do is convert any real number to a dual number. And we'll read the right-hand side first. I'm just going to convert it by calling the constructor for dual, by telling it that the val piece is whatever my real number was, and the epsilon piece is 0. Right? Same thing you do with a complex number. How do you convert the real number 1 to a complex number? It's 1 times 0i. Same idea. Now, the trick here is, let me make this more explicit. This is a dummy variable that I don't need the name for, so I'm omitting it. You see this idiom in Julia code. This type that's a parametric type is confusing, and I want to say this correctly. Type, curly braces t, is a type with one element, and that is the data type t. So type dual here is a type of which dual is the only element. This is really just how you say, if somebody calls this with dual, what this means is, if I call convert dual 5 or 4, it goes here. This is a fancy way of saying only if this thing is the type dual. Does that at least explain what the purpose of this is? Okay. And then I'm going to define this for it being a dual number. The reason I have to do this, and this is where reasoning about the type system and ambiguities gets tricky, is because dual is itself a real, and I get a recursion here if I try to take the dual of a dual. Because if I don't define this guy, and I try to convert a dual to a dual, then it calls the dual constructor on it again, and it tells me I can't convert my dual back to a float 64. So again, these ambiguities get a little bit tricky. So this is a corner case. These are the two things I need. And what will happen now is that Julia will handle all the implicit conversions from reals and ints and floats and all that stuff to dual. And it'll just work. The other thing that's really handy, even if it just saves you like a factor of 2, there's a thing called promote rule. And promote rule says, when I have two types and I need to do something with it, what is the next widest type that accommodates both of them? So here is this, again, this type idiom, and I say, oh, if I have a float 64 or an int64 or a float 32, there are less verbose ways to probably write this that are more generic, but I'm just spelling this out. If I've got those things, so I feed the promote rule float and dual, and it gives me back dual. It says dual is big enough to handle any float 64. Dual is big enough to handle any int64 or float 32. Again, you could think about having this with a parametric thing t, which says if you give me any t that's a real number in a dual, I give you back dual. So I kind of wrote this out, but you could do it more succinctly at the cost of notation.
Does the order matter?
No, it doesn't, which does really save you here. Because really we're asking about a relationship among types and not whether the relationship is commutative.
Is that a listable thing so that within the curly brackets you could have a list of float 64, int 64, and float 32?
This is something I didn't have time to cover. The question is, could I have any of these here? And I think what I would have to do is use union. Union is one of these weird kind of special case types in Julia where you say, oh, if something is a vector or a matrix, that's cool. That's a type, and it is the union of two type classes. I think what you would have to do in this case, though, I without trying it, I'm not sure I'm willing to guess, is you'd have to do it like this. I don't know that type takes multiple parameters, but I would have to do, type in 64. I think that's what you would have to do.
Got it.
And that saves you some space. Okay, here's the other idiom for this is import base, and I'm going to import a bunch of things that I just want defined, right? This is all the stuff you do in C++ if you wanted to define these things. I need plus, and I need minus, and divide, and times, and absolute value, and less than and equal, and less than or equal to. That's kind of our minimal set of things that are arithmetic types. And I'm doing all the normal stuff. Don't get too bogged down in this. If I add two duals, I add the vowels and the adjoints. Unary minus works this way. Notice that the difference between unary minus and subtraction is just how many things you call it with. They have the same name. And I use the unary minus to define, this is like kind of cute math. If I have these two things, this gets called. Note also that this indirection doesn't really hurt you much. Normally you'd be worried, oh, this is two function calls every time. But it really doesn't end up being, because the first time you call this thing, it gets compiled, and then your compiled function, your compiler is probably smart enough to elide those two function calls. Multiplication gets a little bit trickier because epsilon squared is 0, and this is the right thing. And division gets trickier because when you divide by the infinitesimal, things are wonky. Absolute value you have to be a little careful with. You compare the big parts, and then you compare the little parts. You do have this ternary operator, which you see, you either love this or hate it. Is this thing true? If so, return this. If not, return this, that you see all over C code. I kind of like it now, but you don't have to use that if you don't want to. Equality. And again, I'm not using the function keyword. I've just got expressions. They return Booleans. And less than or equal. And then the last thing I'm going to do is import the logarithm function. Now, all this is just to make sure that stuff works like it should. And I'm going to import this file in a second and show you what you can do just having defined these things. I'm going to define log. And what I need to tell this is that log of a dual returns the log of the value part plus the epsilon piece over the value part, which is the derivative of the log, right? The derivative of log x is 1 over x. So this is kind of the directional derivative of log. There's a package called calculus.jl which has derivatives for like 50 univariate functions, and Jared is really smart and just auto-defines these with a macro that writes the code. It sort of loops over all the functions in calculus and writes the appropriate code to do this. So forward diff knows how to differentiate everything that calculus does. Calculus.jl. So I want to now go back to my thing here, and let's go back to Julia. And I just want to run that code. In Julia, this is include. And include just sort of runs your script. It's like the %run magic in IPython. And I will demo for you a couple of things this will do, and then we'll be done. So things that you get, okay, just to show you that things work. Right, my show works nicely, my Unicode works nicely. Right, this is just sanity check, right? Because I defined all these things. But I can have an array of duals. That works just fine. They're all zeros. The conversion happened automatically. I'm going to do all the element-wise broadcasting is going to work. So I'm here taking a random matrix and multiplying epsilon, which is dual of 0, 1, by a dual array, which all has element 0, and like everything works. But interestingly enough, functions like minimum works and maximum works. This is kind of the beauty of having a language where you aren't having to get an escape hatch to C to make numeric types work. Is because things like minimum and maximum are defined in Julia itself, I get a lot of stuff.
How'd you get that without overriding?
Because I had less than or equal to an absolute value.
Oh.
It's turtles all the way down. And this is my best trick. Backsolve works too. And no, I got close on that one. If anybody knows what the singular value decomposition is. So there's actually a lot of linear algebra that now just works because it's defined in Julia. So if you wanted to do linear regression on these things, like, you can calculate that. And just to show you that now what I can do is I'm going to define a function that's kind of dumb. This function takes 2 arguments. It takes the log of their sum and subtracts the first argument. So this is something you might have in a model. And now what I can do is give it an input. So let's say what I really care about at first. All right, so that's our base value. Now what I want to do is I'm going to make a dual number which substitutes the first argument with 1 plus epsilon, right? I'm going to take a derivative in the direction of x. So the derivative in the direction of x is 0.33, and you can verify that. And now what I'm going to do is give you the other one, 2 plus epsilon, and that's the other derivative. So you can imagine that it's now pretty easy to take all these functions that you've got. And remember, I didn't just have the log function I defined this for. I was composing functions. I can have loops on these things. I can have branches in my code, and it all still works, which is the beautiful thing about forward mode that reverse mode doesn't have. This is how forward diff works, essentially, is you define a number type. It's a very small package, and there's a lot of extra stuff that's defined there. But this, I think, kind of shows you the power for a system that works as long as we don't overtype it. Right? So this works for any place I'm allowed to drop in a real number, which is why I encourage you not to pepper your code, your function definitions with like float 64s, unless it only works for float 64s, is because this sort of generic programming becomes really possible. We are in the process of doing this, say, for the distributions package in Julia, where everything was float and in 64. We now have parameters on everything. So if you want a normal distribution that takes dual numbers so that you can calculate expectations and sums with respect to distributions and take derivatives of functions defined that way, which I do in my research, that now works. So almost everything in the distributions package now, if you do some sort of Bayesian inference and you have an objective function that you want to take a gradient with respect to, that can be done. It just passes right through the distributions and no explicit derivatives required. So it really is a powerful system, but it takes a little getting used to. So I'll leave this code up if people have questions about this. But again, this is not as robust as you'd want it in production, but it's under 30 lines of code to essentially define a new number type. So that's my material. I'm happy to take questions Thanks for paying attention, and yeah.
My apologies for not getting all the other questions on the mic, but we're going to try now. The other thing is the facility folks have to turn the rooms back into get ready for the general session, which means they're taking down the tables, moving all the chairs, putting up a lot more chairs. So they've asked us to be out of this building by 5:30. So as soon as this wraps up, what I'd encourage you guys to do is move over to the tents. It's a beautiful day, relax, but we can definitely take up until 5:30. But then I'd ask you to move along. So we had a question right up here.
So you did something a while back you didn't explain. You passed as a parameter to a function :x, and then
Yes.
it got printed out as variable named x. Can you tell us what that is?
Yeah, I'm trying to think of a succinct way to say it. So it's a symbol, and what you really want, okay, I'm going to tease this just a little bit. In a language like Lisp does this, so in a language where the code itself is an object in the language, and I think the term is homoiconic, we need a way to represent Julia code inside Julia. So if I do something like this, I'm not actually showing you my screen. If I do something like this, this colon parentheses is Julie's way of saying quote. In other words, take this expression, interpret it as code. Don't evaluate it. I can do something called dump. And this is actually the structure of the code that the Julia parser gets. So if you're used to S expressions in Lisp, it tells me that the symbol for this is a call, and it's calling plus with arguments x and 2. So it's a tree-structured S expression thing. The key thing is, if I'm going to generate code inside this quote, I need to be able to tell the difference between a string with the string that has the x character in it and something that I should interpret as a variable in the system. That :x, you should think of as quote x. It's the symbol for x. It says x is going to be a variable in the environment. And so symbols are used in Julia as keys in dictionaries a lot because they're immutable, and they often do things we do with strings. And I'm sorry that's a little rushed, but if you have a follow-up, that'd be great.
Okay, my first guess would have been that it was a way to maybe refer to that variable to like modify the value of the variable from in the enclosing scope. But you're saying
Yeah.
that's not that at all.
It's
Okay.
unrelated. It just says this is x and it's a symbol in my program.
What other questions? Yeah. I scared. Oh, good. Kyle's got one.
So when you're using Julia in like an application environment with other services, what kind of like interoperability features does it expose? Like, can you execute C or Python code, or can you send it, information over a network?
Plays nicely with Python.
Sorry, it's recompiling my cache files. The answer is, it's going to break. The answer, that's because I'm not using this version every day. The answer is for C, there's basically no boilerplate code. You're just calling it, and you have to give the symbol for the function name instead of the function name in a string. C++ you can now have interoperability with, which is a crazy hard feat, but a couple of people have done it to have call between C++ and Python, or C++ and Julia. Python, there's a great package called PyCall, which essentially wraps all the Python classes. And if I had been able to do that, I could have done this, and I would have all the NumPy functions. And you can use, probably still the most popular plotting library for Julia is matplotlib, accessed through PyPlot is what it's called. So I would say R is really good now because there's an R REPL mode and people have got that working. Python is really, really good. C and C++. You can embed the Julia interpreter in the same way that you can embed the Python interpreter. The status of what people have done with that is a little bit hit or miss, and I'm not an expert there, but these things are at least possible. And in the case of PyCall, it's actually quite smooth.
Any other questions? Yes. Eric, do you really have?
Hi. In Python, there's been a bit of interest lately with optional static typing, just to give you some type inference
Yeah.
before runtime. Anything like that in Julia?
So I'll give you two answers. One is that the type information we provide, the compiler strongly relies on. So I would say that's intrinsic to the way Julia thinks about things, because the compiler is making assumptions based on the fact it knows a variable is an integer. So you're not really providing type hints, it's that your code is literally being compiled. The other aspect of it, though, is there's been some interest in static compilation, so making an executable that would be a standalone executable. Somebody did that as a proof of concept, but it's not trivial, because what you end up having to do is bundle the Julia runtime. Because it's not just that Julia is like Python and C++ blended together in a sense, right? Because it's capable of interpreting your code as it goes, but it's also doing a pass where it takes your code and makes it simpler, and then feeds it to LLVM, and then has bytecode, and disentangling all that is still a little tricky. So people have done that, but it's not. It takes some fiddling to do. So I think what you should think of is that in terms of things like Numba, where you have to give type information, that's really what Julia is doing by virtue of the fact that your code is always getting compiled.
Thanks.
Last question? Any last questions? Scared everybody away. Thank you so much, John.
Thanks.